Okay, so in part 3 of chapter 8, we're looking at centripetal force, centrifugal force, simulated gravity. So the idea is that a centripetal force is a force that causes objects to go into orbit, basically, to go in a circle. So this time the entire object is revolving around a point. And so you could think of a yo-yo that you're swinging around, a ball on a string. Well, what force is there when you are swinging a ball around? Well, the only force that you have available really is the tension. So you are pulling on the object, with tension along the string. Now, there's also, of course, gravity. Um, but mostly we're going to ignore gravity for the purposes of this discussion at the moment. And we're just going to think about the force of the tension that's here. So the tension is what you pull with. And that provides a force which is called the centripetal force. Centra for towards the center, and center seeking is what that means, centripetal. So force towards the center. Now, remember that forces can cause accelerations, and accelerations are changes in a velocity. And a long time ago, we said velocity could change by speeding up, slowing down, or changing direction, because an actual velocity, not just a speed, but a velocity has a direction. In this case, a centripetal force, the speed stays the same, but what we're doing is changing the velocity by changing the direction. And so what we're actually doing is causing an acceleration. So the force towards the center is causing an acceleration, and that changes the velocity to a new direction while keeping the speed the same. So we've changed the direction. And so that keeps happening. There's an acceleration, and that changes the velocity. Acceleration changes the velocity. And so all the way around the circle, the ball keeps experiencing an acceleration, and each time that causes a change in its velocity direction. Okay, so that's what's going on here. This force changes direction, but the speed stays the same. Now, there's a formula for this, which is the force centripetal equals mv squared over r. So let's say we've got a velocity here of 10 meters per second, and the radius is 5 meters, and we have a mass of 2 kilograms. Okay, so we would just put that into the formula. 2 kilograms, 10 meters per second. And don't forget to square it. That's what people often do. They forget the square. Divide by the radius of 5 meters. And so we're going to get 2 times 10 squared, which is 2 times 100. And we're dividing by 5. So that's going to be 2 times 20, which is going to come out to be 40. Now, this actually will come out to units of force, so it will come out to newtons, because you have kilograms, meters per second, that gets squared, so that's meters squared over seconds squared. And then you've got an additional meter. So what happens is that it turns out to be the same units as you would get for your normal acceleration. So, so anyway, so it turns out to be still newtons, okay? So kilograms, meters over seconds squared. Mass times acceleration. So Now, if you have a 1 kilogram weight swinging in a 1 meter circle at a speed of 1 meter per second, well, by that formula, of course, mv squared over r, that's going to be 1, 1, 1. So we're just going to end up with 1. But if you double the weight, or the mass, then you're going to have 2 times 1 squared over 1. So that's going to be 2. What happens if you double the speed, but leave everything else the same? That's going to be 4. And if you double the radius, then you end up with 1/2. Okay, so the big change there, of course, is if you double the speed because of the square, then you're going to get 4 times as much force. But also doubling the weight, right? This is why school buses aren't very good at taking turns. It needs a lot of force if you've got a lot of mass. And if you double the radius, then you don't need as much force. So hairpin turns are difficult for a car to take. A large, gentle curve, that's easy. And where does that force come from? Well, when you're driving, your tires are, when you turn your steering wheel, your tires basically are rotating. You push them over, and what happens is that they are, you don't think of it, but they're kind of hitting the road. I can't get this to draw. Let me put that another color. So your tires, as you turn to follow the road, basically your car hits the tires, and is bouncing towards the center. So the tires are giving you the frictional force that you need to actually stay on the curve. Okay, so you're turning your wheel so that your tires are basically interfering with going straight. And so that provides the centripetal force that you need. And if you don't have friction between the tires and the road, then you're not going to be able to bounce towards the center. Okay, so let's look at these different cars. What's their centripetal force direction? Well, for car A, its curve is like that, so its center must be here, right? And car B is going around the same curve, but yeah, its centripetal force must be that direction. Car C is going around this point, so its force would be that direction. Car D, well, it's going straight, so it doesn't need a centripetal force. What's the force for an 8,000 kilogram car to go around a 10-meter curve at 10 meters per second? Easy to find out. And so 8,000 kilograms, 10 meters per second squared, divide by 10, and we're going to get 80,000 newtons of force. A lot of force to make a fast car. But it's not going very fast. 10 meters per second is about 20 miles per hour. Well, if you're driving on a normal road, yeah, you want to get down to like 10 miles per hour to take most turns. So actually, this is fast for a normal driver to take a turn, but it's not fast for a race driver. Of course, one thing with race cars is often these Formula One cars and stuff, the track is slanted. That helps push them towards the center. But yes, if they're going faster, which they would be, let's say we triple the speed, what's going to happen then? Well, of course, as you triple the speed, then what's going to happen is that that's going to get squared. So by tripling the speed, that's going to be 9 times as much force. So we're going to end up with 720,000 newtons. Yes, so this is why you shouldn't take turns at double or triple the speed they're rated for, because the force goes up as the square of that. And so it's incredibly dangerous. Now, what happens if there's ice on a road? Well, if there's ice, you don't have friction, and then you don't have the ability to avoid what's coming. And so, of course, there was that horrible, horrible crash in Texas this year. When they had the freeze down there was a really tremendously horrible collision, and YouTube has horrifying videos of it. Anyway, so yes, so you've got lots of videos nowadays of cars crashing due to lack of friction, ice on the road. Okay, now if you're in an airplane and you want to make a loop-de-loop, well, you need a force that points towards the center. So the thing is that if you are the person in the airplane, you have to experience that force too. So you will experience that force against your bottom, right? So that will feel where you're going to feel the force. And so it's towards the center of the circle. Now that force is going to be greater than the weight of the person. And so that's where we talk about G's of force. It's multiples of the weight or multiples of the acceleration of gravity. Now in this case, the person is doing the loop-de-loop the other direction. And what's happening here, I'm sorry, that is the same direction, but it's okay. It's harder to go usually the other direction, where you have to curve, like where you're curving so that your airplane is flying like this. So you, if you were sitting in there, your force would be pulling downward on you towards the center of a circle. Anyway, so here we've got this pilot who needs to experience that centripetal force towards the center of the circle. And so how much force would that be? mv squared over r. We've got the centripetal acceleration is 50 meters per second squared. And so we've already got that. How many G's of force would that be? And what is the centripetal acceleration? Well, the centripetal acceleration is where you've got the force is mass times acceleration. So basically I can kill the mass in here and get 50 meters per second squared for just the acceleration of this. So cross out the mass. This would be the acceleration that's needed. And now that I know that it's 50 meters per second squared, how many multiples is that of G? Well, I can take the 50, divide by 10, and that means this pilot is experiencing 5 Gs. Now, 5 Gs is bearable. Sometimes people start to have issues at 6, 7, 8, 9, 10 Gs. They'll start to get black out, 12 Gs. And so, yeah, so usually you do not want to go very high. And so sometimes pilots do black out in tight turns, right? Reduce the radius, and that actually will increase the force. And roller coasters, same thing. So roller coasters will sometimes take you up to 3 Gs or more. Now there's a counterpart to this, which is called the centrifugal force. The centrifugal force, and I say it strongly fugal so you can hear the difference, is pointing away from the center, counter center. And it's a reaction force. So some people think this is an independent force by itself, but we have it there. It isn't. It's just a reaction. And that's using Newton's third law. So when we've got a string pulling on the ball, that's the centripetal force. But the ball also pulls on the string, right? So the ball pulls on the string. So force of string on ball, force of ball on string. And so it only exists as long as the ball is rotating. And so the string is taut outwards because of that. But if you cut the rope, then that centrifugal force disappears as the centripetal force disappears. So here we've cut through them. No more force inwards, there's no more force outward, and the ball just goes straight. So some people think the ball is going to go outward with the outward velocity, but there's no force to push it outwards. And all it has is its leftover velocity because if it was moving around the circle, now it's moving in a straight line. So it no longer follows a circle because there's no force to make it go that direction. There's no force pushing it outward. So it just goes straight. So you can try this at home, swing something around, and then it might be your headphones or something. Anyway, but when you let go, so I'm going to let go when it is at just over my head. And in that case, because it's circling this direction, it should go that direction, okay? So I'm going to swing it and hopefully let go. Whoop, at the right time. Yep, I went that way. Okay, so somewhere. All right, so that's the idea. It just keeps going with inertia. Now, in this chapter also is talking about a bug in a can. So imagine there's a bug down here in this can that you're swinging around your head. There's the bug. Now the bug feels a force on its feet, pushing it towards the center. That's the can, right? The bug would just go in a straight line, but it is pushing, as it tries to go straight, it pushes against the can. And so it pushes on the can pushes back on it, and so it experiences a centripetal force. Now, the idea is that we could cause what's called simulated gravity. The simulation is the idea that that force against our feet is what we experience as gravity, as a gravitational field, because we're pulled down by gravity, and then we hit the surface of the earth, and then that surface of the earth has a normal force that pushes us the other direction. So that's what we feel as gravity, that force against our feet. The idea is that we could have a space station that could rotate at such a speed that the centripetal force would be equal to the force of gravity, or maybe a little bit less. And the idea is our bodies wouldn't really know the difference. So we would be inside the space station, we would experience a centripetal force, that's the normal force against our feet, and the centrifugal force, the reaction force, to us, that would be like there was a gravitational force. And so the idea is that the bugs could live inside this tire their entire lives, not knowing that it was rotating. Would it work for humans? Again, the centripetal force would be that normal force against our feet. So our inertia wants us to continue going in a straight line, but we hit the tire. So because of that, we feel a force against us, a normal force. And so that inertia keeps pushing us against the tire, and so we would have a centrifugal force that we would think of as our gravitational force. Now, so everything you do in here should be able to be the same. So if you drop a ball, whoops, if you dropped a ball out of your hand, it should fall at your feet. How does that work? Well, the idea is that if you were dropping a ball out of your hand, it would have velocity as you let go because it was spinning with you. So it would have a straight line velocity, a tangential velocity. And so it would have that inertia. And so then it would be moving in a straight line, but you are being forced to go in a curved line. And eventually the ball would end up smacking into the side of the tube that you're in, same time as you reach that point. So it would be like the ball to you seemed to just fall straight down out of your hand onto the ground, because remember, you don't know you're rotating. And so to your point of view, the ball would look like it just fell right down out of your hand. So this is sort of what the interior of a space station might look like. And you can see there's running water. You could have a river that, because water too would flow like normal. Trees would grow upwards against the simulated field of gravity, and everything would be normal. So it is possible. So if you've ever seen 2001 Space Odyssey, it starts out with that spinning space station, providing a gravitational force. And you need a gravitational force out in space because low G causes your bones to stop gaining mass. And they start to lose mass up to 2% of bone loss per month. Okay, so that's as far as we're going on this part. And so, stop recording.